1915, Albert Einstein reshaped our understanding of the cosmos. Gravity, he said, isn't a force pulling through space. It is the curvature of space-time itself, and changes to this curvature ripple outward at the speed of light. But could gravity travel faster than light? Does it obey the same limits, or do we still misunderstand its nature? Einstein said no, yet as physics advances, the question lingers and may hold profound consequences for our understanding of the universe. When we look up at the night sky, we see stars whose light has traveled for years to reach us. But what about their gravitational pull? If the sun suddenly vanished, would we feel the loss of its gravity instantly, or would we have to wait 8 minutes and 20 seconds, just like we would for its light to disappear? This isn't just academic curiosity. The speed of gravity touches the very foundation of how reality works. It connects to the deepest questions about causality, the nature of space and time, and whether the universe has hidden shortcuts we haven't discovered yet. From the collision of black holes billions of light years away, to the theoretical possibilities of faster than light travel, gravity's speed limit shapes everything we know about the cosmos. Tonight, we'll explore this silent question that has puzzled physicists for over a century. We'll journey through Einstein's insights, witness the birth of gravitational wave astronomy, and peer into the speculative edges where physics meets the impossible. Along the way, we'll discover why this seemingly simple question about speed has such profound implications for our understanding of reality itself. The universe is vast, mysterious, and bound by rules we're still learning to understand. The speed of gravity is one of those rules, and it may be more important than we ever imagined. Before Einstein, gravity was simple. Newton had given us a universe where massive objects pulled on each other across empty space, instantly and without delay. The sun tugged on Earth, Earth pulled on the moon, and everything happened at once, no matter how far apart the objects were. It was elegant, predictable, and completely wrong. Einstein's revolution began with a simple observation about falling. If you're in a windowless elevator and someone cuts the cable, you'll float weightlessly as you plummet. You can't tell the difference between floating in deep space and falling freely under gravity's influence. This equivalence principle led Einstein to a startling conclusion. Gravity isn't a force at all. It's the shape of space and time itself. Imagine space-time as a vast rubber sheet stretched tight. Place a bowling ball in the center and it creates a depression. Roll a marble nearby and it will curve toward the bowling ball, not because of some mysterious pulling force, but because it's following the straightest possible path through curved space. This is how planets orbit the sun, how light bends around massive objects, and how gravity works throughout the universe. But here's the crucial insight that changed everything. If you suddenly move that bowling ball, the depression doesn't instantly reshape across the entire sheet. The change travels outward as a wave, moving at a specific speed. In space-time, that speed is the speed of light, roughly 300,000 kilometers per second. This isn't just a coincidence. It's the speed at which cause and effect can travel through the universe. Einstein called these traveling disturbances gravitational waves. Picture two massive black holes spiraling into each other billions of light years away. As they dance their final dance, they create ripples in space-time itself. These ripples spread outward like waves on a pond, carrying energy and information about the cataclysmic event that created them. They travel at exactly the speed of light, no faster, no slower. This speed limit isn't arbitrary. It's woven into the fundamental structure of reality. Nothing can carry information faster than light, not even gravity. If it could, we'd live in a universe where effects could precede their causes, where time itself would lose meaning. You could theoretically send a message to your past self, creating paradoxes that would tear apart the logical structure of existence. The mathematics of general relativity are crystal clear on this point. Gravitational effects propagate at the speed of light, because space-time itself can only transmit changes at this rate. When Einstein published his field equations in 1915, he embedded this speed limit directly into the fabric of his theory. Every prediction that followed, from the bending of starlight during solar eclipses to the precise orbit of Mercury, depended on this fundamental assumption. But proving Einstein right took nearly a century of increasingly sophisticated observations. The effects of gravity's finite speed are incredibly subtle in most circumstances. When you drop a ball, you don't notice any delay because Earth's gravity well is already established. The ball follows the curved space-time that's already there, created by our planet's presence over billions of years. The real test would come from events violent enough to create detectable changes in space-time itself. Events like the collision of black holes, the explosion of massive stars, or the chaotic dance of neutron stars spiraling to their doom. These cosmic catastrophes would create gravitational waves strong enough to detect if we could build instruments sensitive enough to catch them. For decades, physicists dreamed of such instruments. They imagined laser interferometers stretching for kilometers, capable of detecting changes in distance smaller than 1/10,000th the width of a proton. It seemed impossible, but the promise was extraordinary. By detecting gravitational waves, we wouldn't just confirm Einstein's prediction about gravity's speed. We'd open an entirely new window into the universe, allowing us to witness cosmic events that remain invisible to all other forms of astronomy. The stage was set for one of the most ambitious experiments in human history. The hunt for gravitational waves would either confirm Einstein's century-old insight or revolutionize our understanding of gravity itself. Either way, it would change everything we thought we knew about the cosmos and our place within it. As we drift deeper into this cosmic mystery, we find ourselves at the threshold of discovery. The universe was about to reveal one of its most closely guarded secrets, and humanity was finally ready to listen. The question that had haunted physics for a century was about to be answered, but the journey to that answer would take us through some of the most extreme environments in the known universe. Einstein had set the stage with his equations, but nature would have the final word. And that word would come in the form of ripples in space-time itself, carrying messages from the most violent events in cosmic history. The universe was about to speak, and we were about to hear gravity's voice for the very first time. From the depths of space, two black holes had been dancing for millions of years, spiraling ever closer in a deadly embrace. Their final moments would create the first gravitational waves ever detected by human instruments, confirming Einstein's boldest predictions and opening a new chapter in our understanding of the cosmos. The age of gravitational wave astronomy was about to begin, and with it, our ability to probe the deepest mysteries of space and time would be forever transformed. The mathematical beauty of Einstein's theory was about to meet the raw power of cosmic violence, and the result would reshape our understanding of reality itself. We were no longer just observers of the universe. We were about to become listeners, tuning in to the gravitational music of the spheres that had been playing around us all along, waiting for us to develop the ears to hear it. This was the moment when theoretical physics would become experimental reality, when Einstein's mathematical poetry would be tested against the harsh truths of cosmic catastrophe. The universe had been sending us gravitational messages for billions of years. We were finally ready to decode them. To understand why this breakthrough was so revolutionary, we need to appreciate just how weak gravity actually is. Of all the fundamental forces in nature, gravity is by far the weakest. The electromagnetic force that keeps atoms together is about 10 to the power of 36 times stronger than gravity. This means that detecting gravitational waves requires instruments of almost unimaginable sensitivity. Consider the scale of what we're trying to measure. When a gravitational wave passes through Earth, it stretches and compresses space itself, but only by an incredibly tiny amount. The strongest gravitational waves we can detect change the distance between 2 points separated by 4 kilometers by less than 1/10,000th the width of a proton. That's like detecting a change in the distance to the nearest star that's smaller than the width of a human hair. Yet this weakness is also what makes gravitational waves so precious to astronomers. Because gravity interacts so weakly with matter, gravitational waves can travel through the universe virtually unimpeded. Light gets absorbed, scattered, and blocked by dust and gas. But gravitational waves pass through everything as if it weren't there. They carry pristine information about the events that created them, no matter how far they've traveled or what they've encountered along the way. This means that gravitational waves can tell us about cosmic events that are completely invisible to traditional astronomy. When two black holes merge, they produce almost no light, but they create powerful gravitational waves that can be detected billions of light years away. When neutron stars collide, they produce both gravitational waves and electromagnetic radiation, allowing us to study the same event with multiple types of instruments for the first time in history. The implications go far beyond just confirming Einstein's predictions. If gravitational waves travel at the speed of light, as Einstein predicted, then we can use them to test some of the most fundamental assumptions of modern physics. We can probe the nature of space and time itself, study the behavior of matter under the most extreme conditions in the universe, and even search for evidence of physics beyond our current understanding. But there's another, more subtle aspect to this story. The speed of gravitational waves doesn't just tell us about gravity, it tells us about the fundamental structure of causality itself. If gravity traveled faster than light, it would mean that cause and effect could be transmitted instantaneously across vast distances. This would fundamentally change how we understand time, space, and the relationship between events separated by cosmic distances. The mathematical framework of relativity is built on the assumption that there is a maximum speed at which information can travel through the universe. This speed limit isn't just about light or gravity. It's about the very fabric of reality itself. It determines how the past, present, and future relate to each other, how cause and effect work across space and time, and how the universe maintains its logical consistency. When Einstein derived his field equations, he discovered that this speed limit was built into the very geometry of space-time. Changes in the gravitational field, like changes in the electromagnetic field, can only propagate at this maximum speed. This isn't a technological limitation or a quirk of our measuring instruments. It's a fundamental property of the universe itself. The discovery of gravitational waves traveling at the speed of light would therefore be much more than just a confirmation of Einstein's theory. It would be a validation of our entire understanding of how reality works at the most fundamental level. It would tell us that the universe is indeed governed by consistent laws, that causality is preserved across cosmic distances, and that the mathematical beauty of Einstein's equations reflects something deep and true about the nature of existence itself. As we prepare to journey into the story of how these waves were finally detected, we're not just exploring a triumph of experimental physics. We're witnessing humanity's first direct contact with the gravitational symphony that has been playing throughout the cosmos since the beginning of time. We're about to hear the universe speak in a language we've never heard before, and that language will tell us secrets about the nature of reality that we've been waiting over a century to learn. On September 14th, 2015, at exactly 9:51 in the morning, the universe whispered a secret that had been traveling for over 1 billion years. Two black holes, each about 30 times the mass of our sun, completed their final dance in a galaxy far, far away. In a fraction of a second, they merged into a single, more massive black hole, releasing more energy in gravitational waves than all the stars in the observable universe were producing in light at that same moment. The ripples from this cosmic catastrophe spread outward at the speed of light, carrying with them the signature of one of the most violent events in the history of the cosmos. For over 1 billion years, these waves traveled through space, passing through galaxies, star systems, and vast empty voids, gradually weakening, but never quite disappearing. They were a message written in the language of space-time itself, and on that September morning, humanity finally learned how to read it. The instrument that caught this whisper was called LIGO, the Laser Interferometer Gravitational Wave Observatory. Two identical detectors, one in Louisiana and one in Washington state, had been listening to the universe for years without hearing anything significant. But on that September morning, both detectors registered the same unmistakable signal within milliseconds of each other. The universe had spoken, and we had finally learned to listen. To understand what LIGO actually detected, imagine trying to measure the change in distance between two cities, when that change is smaller than 1,000th the width of a proton. That's essentially what LIGO accomplished. Each detector consists of 2 arms, each 4 kilometers long, arranged in an L shape. Laser light bounces back and forth between mirrors at the ends of these arms, creating an interference pattern that's incredibly sensitive to tiny changes in the arm lengths. When a gravitational wave passes through the detector, it stretches space in one direction while compressing it in the perpendicular direction. This causes one arm to become slightly longer while the other becomes slightly shorter. The laser light takes a tiny bit longer to travel down the stretched arm, and this difference shows up as a change in the interference pattern that can be measured with extraordinary precision. The engineering challenges were staggering. The mirrors had to be suspended in perfect isolation from every possible source of vibration. Earthquakes, truck traffic, ocean waves, even the thermal motion of atoms in the mirror supports could overwhelm the gravitational wave signal. The laser system had to be incredibly stable, the vacuum system had to be nearly perfect, and the entire apparatus had to be shielded from electromagnetic interference. But the most remarkable achievement was the sensitivity itself. LIGO can detect changes in distance that are 10,000 times smaller than the width of a proton. To put this in perspective, if the distance from Earth to the nearest star were monitored with the same precision, LIGO could detect a change smaller than the width of a human hair. It's as if we built a ruler capable of measuring the diameter of the entire solar system to within the thickness of a piece of paper. The signal that LIGO detected on that September morning was exactly what Einstein's equations predicted. It started at a low frequency, about 35 cycles per second, and swept upward in frequency and amplitude as the 2 black holes spiraled closer together. The pattern matched theoretical predictions with stunning accuracy. The frequency increased according to the precise mathematical relationship derived from general relativity, and the amplitude grew in exactly the way Einstein's equations said it should. But this first detection was just the beginning. Within days, physicists around the world were analyzing the data, extracting every possible detail about the cosmic collision that had created these waves. They could determine the masses of the 2 black holes, the distance to the merger, the orientation of their orbital plane, and even the amount of energy released in the final collision. The analysis revealed an event of almost incomprehensible violence. In the final fraction of a second before merger, the 2 black holes were orbiting each other at about half the speed of light. The gravitational waves they produced carried away energy equivalent to the mass of 3 suns, all released in a burst lasting less than 0.2 of a second. For that brief moment, the collision produced more power in gravitational waves than all the stars in the observable universe were producing in light. This first detection was followed by others. Each new signal taught us something different about the universe. Some came from smaller black holes, others from larger ones. Some were nearby, others were incredibly distant, Each detection was like tuning in to a different station on the gravitational radio, revealing a hidden symphony of cosmic violence that had been playing all around us throughout the history of the universe. The most sophisticated measurements came from studying the waveforms themselves. Each gravitational wave signal is like a fingerprint, encoding precise information about the masses, spins, and orbital characteristics of the objects that created it. By analyzing these patterns, scientists could reconstruct the final moments of cosmic collisions with extraordinary detail, watching as objects millions of times more massive than Earth spiraled to their doom in the ultimate gravitational ballet. The technology behind these measurements pushed the boundaries of human engineering. Each LIGO detector required innovations in laser physics, materials science, vacuum technology, and vibration isolation that advanced multiple fields simultaneously. The mirrors themselves are among the most perfect objects ever created by humans, polished to a smoothness that would leave bumps no larger than a few atoms if scaled up to the size of Earth. The data analysis presents its own staggering challenges. Gravitational wave signals are buried in noise from countless sources, from quantum fluctuations in the laser light itself to seismic activity on the other side of the planet. Finding these signals requires computational techniques that can sift through enormous amounts of data, looking for patterns that match theoretical predictions with exquisite precision. But the most important measurement was yet to come. In August of 2017, LIGO detected gravitational waves from a completely different type of source. Instead of black holes, these waves came from the collision of two neutron stars, objects so dense that a teaspoon of their material would weigh as much as a mountain. Unlike black hole mergers, neutron star collisions also produce enormous amounts of light, gamma rays, and other forms of electromagnetic radiation. This was the moment physicists had been waiting for. When the gravitational waves from GW170817 arrived at Earth, telescopes around the world turned toward the source location. Within hours, they spotted the optical counterpart, a bright flash of light in a galaxy 130 million light-years away. For the first time in history, the same cosmic event was observed in both gravitational waves and light. The timing was crucial. The gravitational waves and the gamma ray burst that followed arrived at Earth just 1.7 seconds apart. Given that this signal had traveled for 130 million years, this tiny difference in arrival time was extraordinarily small. It meant that gravitational waves and light had traveled at essentially the same speed across cosmic distances, exactly as Einstein had predicted. This measurement was far more precise than anyone had dared hope. The speed of gravitational waves matched the speed of light to within 1 part in 10 to the power of 15. That's like measuring the distance from Earth to the Moon and finding that it agrees with the expected value to within the width of a single atom. It was one of the most precise confirmations of Einstein's theory ever achieved. The precision of this measurement has profound implications that extend far beyond confirming Einstein's predictions. It tells us that the fundamental speed limit of the universe applies equally to gravity and light. This speed limit isn't just a property of electromagnetic radiation or gravitational waves individually. It's a property of space-time itself, a universal constant that governs how quickly information can travel through the fabric of reality. This universal speed limit has consequences that ripple through every branch of physics. It means that cause and effect have a maximum propagation speed, that simultaneous events can only be defined relative to a particular observer, and that the past, present, and future have a definite relationship that cannot be violated even by the strongest gravitational fields in the universe. The discovery also validated decades of theoretical work on gravitational wave physics. Scientists had spent years developing sophisticated models of how black holes and neutron stars behave during their final moments, creating computer simulations that could predict the precise waveforms that different types of collisions would produce. The agreement between these predictions and the actual LIGO data was remarkable, confirming our understanding of gravity in the most extreme environments imaginable. Each new detection adds another piece to the cosmic puzzle. LIGO has now detected dozens of gravitational wave events, each one teaching us something new about the universe. We've learned that black hole mergers are far more common than previously thought, that neutron stars can have exotic compositions and behaviors, and that the universe is filled with a constant background hum of gravitational waves from countless distant sources. The sensitivity of modern detectors continues to improve with each upgrade. Advanced LIGO can now detect gravitational waves from sources billions of light years away, and future space-based observatories will extend our reach even further into the cosmos. We're rapidly approaching a time when gravitational wave detections will be routine, providing a continuous stream of information about cosmic events that would otherwise remain completely invisible. But perhaps the most remarkable aspect of gravitational wave astronomy is what it reveals about the nature of scientific discovery itself. For over a century, Einstein's prediction of gravitational waves remained purely theoretical, a mathematical consequence of his equations that seemed impossible to verify experimentally. The idea that we could detect changes in space-time smaller than a fraction of a proton seemed like science fiction. Yet through a combination of theoretical insight, technological innovation, and sheer determination, humanity has learned to listen to the gravitational music of the cosmos. We've built instruments sensitive enough to detect the aftermath of cosmic collisions that happened billions of years ago, and we've used these detections to test our most fundamental theories about the nature of space, time, and gravity. The universe has always been filled with gravitational waves, ripples in space-time created by every accelerating mass, from orbiting planets to colliding galaxies. But until recently, we were deaf to this cosmic symphony, aware of its existence only through the mathematical poetry of Einstein's equations. Now, we can hear it directly, and what we're hearing is transforming our understanding of the cosmos. As we continue to refine our gravitational wave detectors and expand our network of observatories around the globe and eventually into space, we're entering a new era of astronomy. We're no longer limited to observing the universe through electromagnetic radiation alone. We can now probe cosmic events through multiple channels simultaneously, combining gravitational wave data with optical, radio, X-ray, and gamma-ray observations to build a complete picture of cosmic phenomena. This multi-messenger astronomy is already revealing surprises. The neutron star collision detected in 2017 not only confirmed the speed of gravitational waves, but also solved a long-standing mystery about the origin of heavy elements. The collision created conditions so extreme that it forged gold, platinum, and other precious metals, scattering them into space to eventually become part of future stars, planets, and perhaps even living beings. LIGO has fundamentally changed our relationship with the universe. We're no longer passive observers of cosmic events that happened millions or billions of years ago. Through gravitational waves, we're experiencing these events almost as they happen, feeling the ripples they create in the very fabric of space and time. We've become participants in the cosmic dance, connected to the most violent and energetic processes in the universe through the subtle vibrations they create in space-time itself. The confirmation that gravitational waves travel at the speed of light represents more than just another successful test of Einstein's theory. It's a validation of our entire approach to understanding the universe through mathematical physics. It shows that the mathematical structures we've discovered really do reflect fundamental truths about reality, that the universe really is comprehensible through reason and experimentation, and that human beings really can understand their place in the cosmic order. As gravitational wave astronomy matures, it will undoubtedly reveal phenomena we haven't yet imagined. We may detect signals from the earliest moments after the Big Bang, observe the formation of the first black holes, or discover entirely new types of cosmic objects. Each detection brings us closer to understanding the deepest mysteries of existence, from the nature of space and time to the ultimate fate of the universe itself. The universe has been singing to us in gravitational waves since the beginning of time. Now that we've finally learned to hear this cosmic music, we're discovering that reality is far stranger, more beautiful, and more interconnected than we ever dared imagine. And this is just the beginning of the symphony. While Einstein's speed limit seems absolute, the universe has a curious way of dancing around the edges of impossibility. There are phenomena in physics that appear to violate the cosmic speed limit, yet somehow manage to respect the deeper principles that govern reality. These apparent contradictions don't break the laws of physics, but they do reveal just how subtle and sophisticated the universe's rulebook really is. Consider the moment just after the Big Bang, when the universe underwent a period of exponential expansion called cosmic inflation. In less than a trillionth of a trillionth of a trillionth of a second, space itself expanded by a factor larger than 10 to the power of 26. Regions that had been in close contact suddenly found themselves separated by distances that light couldn't cross in the entire age of the universe. This sounds like a clear violation of Einstein's speed limit, but it's actually something far more subtle. During inflation, space itself was expanding faster than light could travel through it. But this doesn't violate relativity because nothing was actually moving through space faster than light. Instead, space itself was stretching, carrying distant regions apart without any object actually exceeding the speed of light relative to its local surroundings. Imagine ants walking on the surface of a balloon that's being inflated rapidly. The ants themselves never exceed their maximum walking speed, but the balloon's expansion can separate them faster than they could possibly walk toward each other. This is what happened during cosmic inflation, and it's still happening today on a much more modest scale as the universe continues to expand. This expansion has profound implications for our understanding of the cosmos. There are galaxies so distant that their light has been traveling toward us for over 13 billion years, yet they're now more than 46 billion light years away because space itself has been stretching during the light's journey. We can see these galaxies, but we could never reach them, even traveling at the speed of light, because the space between us is expanding faster than we could cross it. But cosmic expansion isn't the only phenomenon that seems to play fast and loose with Einstein's speed limit. In the quantum realm, particles can exhibit a spooky connection that Einstein famously called spooky action at a distance. When two particles become entangled, measuring one instantly affects the other, regardless of how far apart they are. This quantum entanglement appears to create instantaneous correlations across vast distances. Einstein was deeply troubled by this apparent violation of his speed limit. He believed that there must be hidden variables, unknown properties of particles that predetermined their behavior, making the correlations only appear instantaneous. But decades of experiments have shown that Einstein was wrong about this particular aspect of quantum mechanics. The correlations really are instantaneous, and there really are no hidden variables determining the particle's behavior in advance. Yet even this apparent faster-than-light phenomenon doesn't actually violate relativity. While the correlations between entangled particles are indeed instantaneous, no information can be transmitted using these correlations. You can't use quantum entanglement to send a message faster than light, because the measurement results on both sides appear completely random until they're compared through conventional, slower-than-light communication channels. It's as if the universe has built-in safeguards to preserve causality, even while allowing these mysterious quantum connections. The entangled particles share a common fate. But this shared destiny can't be exploited to circumvent the fundamental speed limit that governs the flow of information through space-time. The mathematics of quantum field theory reveals even stranger possibilities. In the vacuum of empty space, particle pairs are constantly popping into existence and annihilating each other in timescales so brief that they can't be directly observed. These virtual particles, as they're called, exist in a quantum limbo where the normal rules of energy conservation can be temporarily violated. Some of these virtual particles appear to travel faster than light, zipping between distant locations in times that would require superluminal speeds. But like quantum entanglement, these apparent violations of the speed limit can't be used to transmit information. The virtual particles exist for such brief moments that they can never carry a coherent message from one place to another. These quantum phenomena hint at a deeper layer of reality, where the classical concepts of space, time, and causality become fluid and ambiguous. At the smallest scales, the universe operates according to rules that seem to transcend the limitations that govern our everyday experience. Yet somehow, these quantum effects always conspire to preserve the larger structure of space-time and the flow of causality from past to future. Perhaps the most speculative, faster-than-light phenomena come from the realm of theoretical physics, where mathematicians and physicists explore the logical limits of Einstein's equations. General relativity doesn't actually forbid faster than light travel in all circumstances. Instead, it reveals exotic scenarios where the geometry of spacetime itself could be manipulated to achieve effective superluminal motion. The most famous of these scenarios is the Alcubierre warp drive, named after physicist Miguel Alcubierre, who first described it in 1994. The concept involves contracting space in front of a spacecraft while expanding it behind, creating a bubble of distorted space-time that could carry the ship faster than light without actually accelerating it through space. The mathematics of the Alcubierre drive are perfectly consistent with Einstein's equations, but the practical requirements are staggering. The drive would require exotic matter with negative energy density, something that may not exist in nature. Even if such matter could be created, the energy requirements would be astronomical, possibly requiring more energy than is contained in the entire observable universe. Similar mathematical constructions include traversable wormholes, hypothetical tunnels through space-time that could connect distant regions of the universe. Like warp drives, wormholes are mathematically possible within general relativity, but they would require exotic matter to remain stable and traversable. The throat of a wormhole would need to be threaded with matter that has negative energy density, preventing the tunnel from collapsing under its own gravitational pull. Even more exotic possibilities emerge from theories that attempt to unify quantum mechanics with general relativity. String theory, for example, suggests that our familiar three-dimensional space might be embedded in a higher dimensional realm, where different physical laws apply. In these extra dimensions, particles and forces might behave in ways that seem impossible from our limited perspective. Some string theory models allow for particles called tachyons, hypothetical entities that always travel faster than light. Unlike normal particles, which approach the speed of light as they gain energy, tachyons would slow down as they gain energy, approaching the speed of light from above rather than below. The mathematics of tachyons is consistent, but their physical interpretation remains deeply problematic. If tachyons existed, they would create severe violations of causality, allowing effects to precede their causes and potentially making time travel possible. Most physicists believe that tachyons, if they exist at all, must be confined to higher dimensional spaces where they can't interact directly with our familiar world. They might influence our reality indirectly, but they couldn't be used to send information backward in time or violate the principle of causality. The search for faster-than-light phenomena isn't just academic curiosity. understanding the limits of Einstein's speed limit could reveal new physics beyond our current theories. If gravity, for example, were found to propagate even slightly faster than light, it would require a fundamental revision of general relativity and might point toward a deeper theory of quantum gravity. Some alternative theories of gravity do predict small deviations from Einstein's predictions, including subtle differences in the speed of gravitational waves. These theories attempt to explain cosmic mysteries like dark matter and dark energy by modifying the laws of gravity on large scales. While none of these theories have been confirmed, they remain active areas of research because they might solve some of the deepest puzzles in cosmology. The study of faster-than-light phenomena also illuminates the profound connection between space, time, and causality. The speed of light isn't really about light at all. It's about the fundamental structure of space-time, the maximum rate at which cause and effect can propagate through the universe. This speed limit ensures that the past, present, and future maintain their logical relationship, that effects follow causes, and that the universe remains comprehensible and predictable. When we explore the boundaries of this speed limit, we're not just pushing the envelope of technology or theory, we're probing the very foundations of reality, testing whether the logical structure of existence is as solid as it appears. Every experiment that confirms the speed limit, every observation that validates Einstein's predictions, strengthens our confidence that the universe operates according to consistent mathematical principles. Yet the exploration continues because the stakes are so high. If faster-than-light travel were possible, it would revolutionize not just physics, but human civilization itself. Interstellar travel would become feasible, communication across galactic distances would be instantaneous, and the isolation that has characterized human existence since the dawn of consciousness would finally be broken. The universe seems to tantalize us with hints of these possibilities while maintaining strict boundaries that preserve the logical structure of space-time. Cosmic inflation shows us that space itself can expand faster than light. Quantum entanglement reveals instantaneous correlations across vast distances. Theoretical physics opens mathematical doorways to warp drives and wormholes. Yet none of these phenomena offer a clear path to practical, faster-than-light travel or communication. Perhaps this is the universe's greatest paradox. It shows us wonders that transcend our everyday limitations while maintaining the fundamental constraints that make existence possible. The speed of light remains the cosmic speed limit, not because the universe is cruel or restrictive, but because this limit is essential to the very structure of reality itself. As we continue to probe these boundaries, we're learning that the universe is far stranger and more subtle than we ever imagined. The apparent violations of the speed limit reveal not flaws in Einstein's theory, but deeper layers of physics that we're only beginning to understand. Each discovery brings us closer to comprehending the true nature of space, time, and causality, even as it reminds us how much mystery still remains. The dance between possibility and impossibility continues, with the universe revealing just enough of its secrets to keep us searching while maintaining the fundamental laws that govern existence. In this cosmic game of hide and seek, the speed of light remains both the ultimate boundary and the key to understanding everything that lies beyond it. As we drift deeper into these mysteries, we find ourselves at the edge of known physics, where established theories meet speculative possibilities, and where the next great discovery might rewrite our understanding of reality itself. The universe has shown us that it's full of surprises, but it has also taught us that even the most exotic phenomena respect deeper principles that maintain the coherence and comprehensibility of existence. The question remains whether gravity, the most mysterious of the fundamental forces, might hold keys to transcending these apparent limitations. While every measurement so far confirms that gravitational waves travel at the speed of light, the story of physics is filled with surprises that emerged just when we thought we understood the rules. The exploration of gravity's ultimate nature continues, and with it, our quest to understand whether the cosmic speed limit is truly absolute, or whether the universe has even greater surprises waiting to be discovered. In the quiet halls of physics departments around the world, a small but persistent group of scientists continues to question one of the most fundamental assumptions of modern physics. What if gravity doesn't follow the same rules as everything else? What if the force that shapes galaxies and bends light might somehow transcend the cosmic speed limit that constrains all other phenomena? These researchers aren't cranks or outsiders. They're serious physicists exploring the mathematical edges of Einstein's theory, searching for cracks in what appears to be an impenetrable wall. The motivation for this search goes far beyond academic curiosity. Our current understanding of the universe is plagued by profound mysteries that seem to demand new physics. Dark matter, an invisible substance that outweighs all ordinary matter by a factor of 5 to 1, has never been directly detected despite decades of increasingly sophisticated searches. Dark energy, an even more mysterious force that's accelerating the expansion of the universe, makes up nearly 70% of everything that exists, yet remains completely unexplained by our current theories. Some physicists wonder whether these cosmic mysteries might be solved, not by discovering new particles or forces, but by modifying our understanding of gravity itself. Perhaps gravity behaves differently on cosmic scales than it does in our solar system. Perhaps the rules that govern the motion of planets around stars break down when applied to the motion of stars around galactic centers, or the expansion of the universe itself. One of the most extensively studied alternatives to Einstein's gravity is called modified Newtonian dynamics, or MOND. Proposed by physicist Mordechai Milgram in 1983, MOND suggests that Newton's inverse square law of gravity breaks down when gravitational accelerations become extremely small. Instead of requiring dark matter to explain the rotation of galaxies, MOND proposes that gravity itself behaves differently in the weak field regime that dominates galactic dynamics. The mathematics of MOND are elegant and surprisingly successful at predicting galactic rotation curves without invoking invisible matter. Galaxies spin as if their outer regions contain much more mass than we can see. But MOND explains this apparent discrepancy by modifying the law of gravity itself. When accelerations drop below a critical threshold, roughly 10 to the power of minus 10 meters per second squared, gravity becomes stronger than Newton or Einstein predicted. This modification has profound implications for the speed of gravitational effects. In standard general relativity, gravitational influences propagate at the speed of light, regardless of the strength of the gravitational field. But in MOND, the modified gravitational dynamics might allow for different propagation speeds, particularly in the weak field regime, where the modifications become important. However, MOND faces significant challenges when confronted with other cosmological observations. While it successfully explains galactic rotation curves, it struggles to account for the large-scale structure of the universe, the cosmic microwave background radiation, and the dynamics of galaxy clusters. Most cosmologists remain convinced that dark matter, despite its elusiveness, provides a more comprehensive explanation for cosmic phenomena than modifications to gravity. But MOND is just one example of how gravity might behave differently than Einstein predicted. Other theories propose even more radical departures from general relativity, including scenarios where gravity might propagate faster than light under certain conditions. These theories are motivated not just by astronomical observations, but by fundamental questions about the nature of gravity itself. One particularly intriguing possibility emerges from theories that treat gravity as an emergent phenomenon rather than a fundamental force. Just as temperature emerges from the statistical behavior of countless molecules, gravity might emerge from more fundamental processes operating at scales too small for us to observe directly. If gravity is indeed emergent, then its apparent speed limit might be a consequence of these underlying processes, rather than a fundamental constraint. Erik Verlinde, a Dutch theoretical physicist, has developed one such emergent gravity theory that attempts to derive Einstein's equations from more fundamental principles involving information and entropy. In Verlinde's framework, gravity arises from the tendency of information to spread out and maximize entropy. Massive objects create gradients in the information density of space-time, and what we perceive as gravitational attraction is actually the universe's attempt to restore informational equilibrium. This emergent approach to gravity raises fascinating questions about the speed of gravitational effects. If gravity emerges from information processing at microscopic scales, then the speed of gravity might depend on how quickly information can be processed and transmitted by the underlying substrate of space-time. This could potentially allow for gravitational effects that propagate faster than light, though such scenarios remain highly speculative. Another avenue for potentially faster than light gravity comes from theories that postulate extraspatial dimensions beyond the three we experience directly. String theory, the leading candidate for a theory of quantum gravity, requires additional dimensions to maintain mathematical consistency. While these extra dimensions are thought to be curled up so small that we can't detect them directly, they might nevertheless affect the behavior of gravity in subtle ways. In some extra-dimensional models, gravity can leak through higher dimensional space, taking shortcuts that aren't available to particles and forces confined to our three-dimensional world. Imagine 2 points on the surface of a cylinder that are far apart when measured along the curved surface, but very close when measured through the interior of the cylinder. Gravity might be able to take such shortcuts through higher dimensional space, appearing to travel faster than light from our limited three-dimensional perspective. The mathematical framework for these extra-dimensional theories is sophisticated and well-developed, but the practical consequences remain largely unexplored. If gravity could indeed take shortcuts through higher dimensions, it might arrive at distant locations before light traveling through ordinary three-dimensional space. This wouldn't violate relativity from the perspective of the higher dimensional space, but it would appear to violate the speed limit from our limited viewpoint. Experimental tests of extra-dimensional gravity theories have so far found no evidence for deviations from Einstein's predictions, but these tests are limited to relatively small scales and weak gravitational fields. The effects of extra dimensions might only become apparent in extreme environments like the vicinity of black holes or during the collision of neutron stars, precisely the scenarios where gravitational wave detectors are most sensitive. Some researchers have proposed even more exotic modifications to gravity that could allow faster than light propagation. These include theories with multiple gravitons, the hypothetical particles that carry gravitational forces, where different types of gravitons might travel at different speeds. Other proposals involve modifications to the structure of space-time itself, creating preferred directions or background fields that could alter the propagation of gravitational effects. Scalar tensor theories represent another class of alternatives to Einstein's gravity. These theories introduce additional fields beyond the familiar metric field of general relativity. The scalar fields can interact with matter and energy in ways that modify gravitational dynamics, potentially allowing for propagation speeds that differ from the speed of light. Some versions of these theories predict that gravitational waves should travel slightly faster or slower than electromagnetic waves, creating testable differences in arrival times for signals from cosmic events. The search for evidence of modified gravity has intensified with the advent of gravitational wave astronomy. Each detection provides a new opportunity to test Einstein's theory against alternatives, measuring not just the speed of gravitational waves, but also their polarization, frequency evolution, and interaction with matter along their path to Earth. So far, Every measurement has confirmed Einstein's predictions to extraordinary precision, but the search continues. Quantum gravity theories offer perhaps the most radical possibilities for faster-than-light gravitational effects. The unification of quantum mechanics with general relativity remains one of the greatest unsolved problems in physics, and the solution might reveal entirely new phenomena that transcend our current understanding of space, time, and causality. Loop quantum gravity, one approach to quantum gravity, suggests that space-time itself has a discrete, granular structure at the smallest scales. Space and time might be composed of finite building blocks, like pixels in a cosmic computer screen, rather than the smooth continuum assumed by classical physics. In such a granular space-time, gravitational effects might propagate by discrete jumps rather than continuous waves, potentially allowing for speeds that exceed the classical light speed limit. String theory offers its own possibilities for faster-than-light gravitational phenomena. In string theory, gravity is carried by closed strings that can move through all dimensions of space, while other forces are carried by open strings that are confined to lower dimensional surfaces called branes. This asymmetry might allow gravitational effects to propagate through routes unavailable to other forces, potentially enabling faster-than-light communication or travel. However, string theory also introduces stabilizing mechanisms that tend to preserve causality even in scenarios that might otherwise allow faster-than-light effects. The theory's built-in consistency requirements seem to automatically prevent violations of causality, suggesting that even if faster-than-light gravitational propagation were possible, it couldn't be used to create paradoxes or send information backward in time. The exploration of these theoretical possibilities is driven not just by scientific curiosity, but by the recognition that our current understanding of gravity remains incomplete. General relativity, despite its remarkable successes, cannot be the final word on gravitational physics. The theory is incompatible with quantum mechanics, fails to explain dark matter and dark energy, and breaks down completely at singularities, like the centers of black holes and the moment of the Big Bang. A complete theory of quantum gravity might reveal that our classical concepts of space, time, and causality are approximations that break down under extreme conditions. The speed of light might not be a fundamental constant, but rather an emergent property of space-time that could be violated or transcended in scenarios where quantum gravitational effects become important. Yet the search for faster-than-light gravity must contend with one of the most robust principles in all of physics, the preservation of causality. Every experiment and observation has confirmed that cause precedes effect, that information cannot travel backward in time, and that the logical structure of the universe remains intact even in the most extreme environments. Any theory that allows faster-than-light gravitational effects must somehow preserve this causal structure, or provide a compelling explanation for why causality appears to be preserved in all observed scenarios. The mathematical tools for exploring these possibilities continue to evolve. Advanced computer simulations can model the behavior of modified gravity theories in scenarios that are impossible to create in laboratories. Sophisticated statistical techniques can search for subtle deviations from Einstein's predictions in gravitational wave data. New mathematical frameworks are being developed to describe gravity in higher dimensional spaces and quantum mechanical contexts. But perhaps the most important tool in this search is the recognition that physics has been revolutionized many times before by discoveries that challenged fundamental assumptions. Newton's absolute space and time gave way to Einstein's relative spacetime. Classical determinism yielded to quantum uncertainty. The solid matter of everyday experience dissolved into fields and particles governed by abstract mathematical principles. The speed of gravity represents another such fundamental assumption. one that has been tested extensively, but never with the precision and scope now possible with gravitational wave astronomy. Each new detection provides another opportunity to search for cracks in what appears to be an unbreakable speed limit. Each measurement pushes the boundaries of our knowledge and tests the limits of our most cherished theories. The physicists who pursue these investigations are not attempting to overturn Einstein's legacy out of disrespect or rebellion. They are following the same scientific impulse that drove Einstein himself to question Newton's absolute space and time. They recognize that every theory, no matter how successful, is provisional and incomplete. They understand that the greatest discoveries often come from probing the assumptions that everyone else takes for granted. As gravitational wave detectors become more sensitive and space-based observatories come online, these searches will intensify. Future detectors will be able to measure gravitational wave speeds to even greater precision, test alternative theories of gravity with unprecedented accuracy, and probe gravitational phenomena in environments that push the boundaries of known physics. The universe may yet surprise us. Gravity, the most familiar yet mysterious of the fundamental forces, might hold keys to understanding dark matter, dark energy, quantum gravity, and the ultimate structure of spacetime itself. The search for faster-than-light gravitational effects continues not because physicists expect to find them, but because the consequences of finding them would be so profound that they cannot afford not to look. In the cosmic game of discovery, the house always wins, but sometimes the players uncover rules that no one knew existed. The speed of gravity represents one such rule, tested and confirmed, but never taken completely for granted. The universe has taught us to expect the unexpected, to question our assumptions, and to remain open to possibilities that challenge our deepest beliefs about the nature of reality. The exploration continues, driven by curiosity, enabled by technology, and guided by the recognition that the universe is far stranger and more wonderful than we have yet dared to imagine. Whether gravity ultimately respects Einstein's speed limit or transcends it in ways we haven't yet discovered, the search itself is transforming our understanding of space, time, and the fundamental forces that govern existence. Imagine trying to time a whisper across the vastness of space, a whisper so faint that it's drowned out by the footsteps of a mouse on the other side of the planet. This is the challenge that faced physicists attempting to measure the speed of gravity. Unlike light, which announces itself brilliantly across the electromagnetic spectrum, gravity speaks in the subtlest possible language, barely disturbing the fabric of space-time, even during the most catastrophic cosmic events. The quest to measure gravity's speed began long before anyone had the technology to succeed. In the late 1600s, Euler Roemer made the first measurement of light speed by observing the moons of Jupiter. Noticing that their eclipses occurred slightly earlier or later depending on Earth's position in its orbit, physicists wondered if similar observations might reveal gravity's speed, but the weakness of gravitational effects made such measurements seemingly impossible with any conceivable technology. The fundamental challenge lies in gravity's extraordinary faintness compared to other forces in nature. The electromagnetic force that binds atoms together is about 10 to the power of 36 times stronger than gravity. This means that while we can easily detect electromagnetic signals from distant cosmic sources, gravitational signals from the same events are almost unimaginably weak by the time they reach Earth. Consider the collision of two stellar mass black holes, each containing the mass of dozens of suns. This represents one of the most violent events possible in the universe, releasing more energy in gravitational waves during the final seconds of merger than all the stars in the observable universe produce in light. Yet when these waves reach Earth after traveling billions of light years, they create distortions in space-time that are smaller than 1/10,000th the width of a proton. Early attempts to measure gravity's speed relied on indirect methods and astronomical observations. In the early 1900s, some physicists proposed timing the gravitational effects of planetary motions, looking for delays that might reveal how quickly gravitational influences propagate through space. But the solar system is essentially a static gravitational environment, where the major bodies move slowly and predictably, making it impossible to detect the propagation speed of gravitational effects. The challenge becomes clear when we consider what would be needed for a direct measurement. To time gravity's speed, we need an event that creates a sudden change in gravitational field, powerful enough to detect across cosmic distances, with a clear beginning and end that can be timed precisely. We also need the same event to produce signals in other forms of radiation, like light or radio waves, that can serve as timing references. Such events are incredibly rare. Most cosmic phenomena either produce gravitational effects too weak to detect, or they produce detectable gravitational effects that change too slowly to provide precise timing information. The collision of black holes produces strong gravitational waves, but black holes emit virtually no light, making it impossible to compare the arrival times of gravitational and electromagnetic signals. The breakthrough came with the realization that certain cosmic events could produce both detectable gravitational waves and bright electromagnetic counterparts. The collision of neutron stars represents the perfect laboratory for measuring gravity's speed. These incredibly dense objects, each containing more mass than our Sun, compressed into a sphere only 20 kilometers across, create powerful gravitational waves when they spiral together and merge. Unlike black holes, neutron star collisions also produce spectacular electromagnetic fireworks. The merger creates conditions so extreme that atomic nuclei are torn apart and rebuilt, forging heavy elements like gold and platinum in a cosmic furnace that briefly outshines entire galaxies. This electromagnetic display provides the timing reference needed to measure how fast the gravitational waves traveled compared to light. But detecting these events required building the most sensitive scientific instruments ever constructed: the Laser Interferometer. Gravitational Wave Observatory represents the culmination of decades of technological development, pushing the boundaries of laser physics, material science, and vibration isolation to achieve sensitivity that seemed impossible just a generation ago. Each LIGO detector consists of two 4-kilometer-long arms arranged in an L shape. Laser light bounces back and forth between mirrors at the ends of these arms, creating an interference pattern that can detect changes in arm length smaller than 1/10,000th the width of a proton. When a gravitational wave passes through the detector, it stretches space in one direction while compressing it in the perpendicular direction, creating a tiny change in the interference pattern that reveals the wave's passage. The engineering challenges were staggering. The mirrors had to be suspended as perfect pendulums, isolated from every conceivable source of vibration. Seismic activity, thermal fluctuations, electromagnetic interference, and even the quantum uncertainty of photons in the laser beam could overwhelm the gravitational wave signal. The vacuum chambers housing the laser beams had to maintain pressures lower than the space between galaxies. Even more challenging was developing the theoretical framework needed to interpret the signals. Gravitational waves from merging compact objects carry incredibly detailed information about the masses, spins, and orbital dynamics of the colliding bodies. But extracting this information requires comparing observed waveforms to theoretical predictions calculated from Einstein's field equations. The computational demands are enormous. Simulating the final moments of a black hole or neutron star merger requires solving Einstein's equations in their full nonlinear glory, accounting for the extreme curvature of space-time near these ultra-dense objects. These calculations push the limits of the world's most powerful supercomputers, and they must be repeated for thousands of different possible scenarios to build libraries of theoretical waveforms that can be compared to observed signals. When LIGO first detected gravitational waves in September 2015, it marked the beginning of an entirely new form of astronomy. But that first detection came from the merger of two black holes, providing no electromagnetic counterpart to measure gravity's speed. The signal confirmed Einstein's predictions about the existence and properties of gravitational waves, but it couldn't directly test whether these waves travel at the speed of light. The crucial breakthrough came on August 17th, 2017, when LIGO detected gravitational waves from the collision of two neutron stars in a galaxy 130 million light-years away. Within seconds of the gravitational wave detection, the Fermi Gamma Ray Space Telescope detected a burst of high-energy photons from the same region of sky. For the first time in history, the same cosmic event had been observed in both gravitational waves and electromagnetic radiation. The timing was extraordinary. The gravitational waves and gamma rays arrived at Earth within 1.7 seconds of each other after traveling for 130 million years. This tiny difference in arrival time, less than 2 seconds after a journey that lasted longer than the time since dinosaurs walked the Earth, provided the most precise measurement of gravity's speed ever achieved. The analysis revealed that gravitational waves travel at the speed of light to within 1 part in 10 to the power of 15. This level of precision is almost incomprehensible. It's like measuring the distance from Earth to the Moon and finding that it agrees with the expected value to within the width of a single atom. It represents one of the most precise confirmations of Einstein's theory ever achieved, and one of the most accurate measurements of any fundamental constant in physics. But achieving this precision required overcoming challenges that pushed the boundaries of experimental physics. The gravitational wave signal had to be extracted from noise that was millions of times stronger than the signal itself. Advanced filtering techniques, developed specifically for gravitational wave astronomy, had to distinguish the subtle pattern of space-time distortion from the countless sources of interference that could mimic or mask the real signal. The electromagnetic observations required coordination between dozens of telescopes around the world and in space. Within hours of the gravitational wave detection, optical telescopes spotted the bright kilonova explosion created by the neutron star merger. Radio telescopes tracked the expanding shockwave as it plowed through the surrounding medium. X-ray and gamma-ray observatories monitored the high-energy aftermath of the collision. This multi-messenger approach to astronomy revealed details about the neutron star collision that would have been impossible to obtain from any single type of observation. The gravitational waves revealed the masses and spins of the merging neutron stars and provided a direct measurement of the distance to the source. The electromagnetic observations showed how heavy elements are created and distributed throughout the universe, solving a decades-old mystery about the cosmic origin of gold, platinum, and other precious metals. The precision of the speed measurement also opened new avenues for testing fundamental physics. If gravitational waves had arrived even slightly earlier or later than the electromagnetic signals, it would have indicated that gravity travels at a different speed than light, requiring a fundamental revision of Einstein's theory. The fact that they arrived essentially simultaneously confirmed one of the most basic assumptions of general relativity. Yet even this extraordinary precision leaves room for subtle effects that might distinguish gravity from other forces. The gravitational waves and electromagnetic signals traveled through different environments during their journey to Earth, potentially affecting their propagation speeds in ways that future observations might detect. The gravitational waves passed through the vacuum of space virtually unimpeded, while the electromagnetic signals interacted with interstellar gas, dust, and magnetic fields along the way. future gravitational wave detectors will push these measurements to even greater precision. The planned LISA mission will place gravitational wave detectors in space, free from the seismic noise and atmospheric disturbances that limit ground-based instruments. These space-based observatories will be sensitive to gravitational waves from sources that are completely inaccessible to current detectors, including the mergers of supermassive black holes and the cosmic background of gravitational waves left over from the early universe. Advanced ground-based detectors are also being developed with sensitivities that will dwarf current capabilities. Future instruments may be able to detect gravitational waves from neutron star mergers throughout the observable universe, providing thousands of opportunities to measure gravity's speed with unprecedented precision. Each measurement will test Einstein's theory in different environments and under different conditions, searching for subtle deviations that might point toward new physics. The development of gravitational wave astronomy has also revolutionized our understanding of the experimental challenges involved in precision measurements. The techniques developed for LIGO have applications far beyond gravitational wave detection, advancing fields from quantum optics to materials science to computational physics. The ability to measure tiny changes in space-time has opened possibilities for detecting other subtle effects, from dark matter interactions to tests of quantum mechanics on macroscopic scales. Perhaps most remarkably, the measurement of gravity's speed has confirmed one of the most profound insights of 20th century physics. The speed of light is not really about light at all. It's about the fundamental structure of space-time, the maximum rate at which cause and effect can propagate through the universe. The fact that gravitational waves travel at this same speed confirms that gravity, like all other forces and phenomena, respects the cosmic speed limit that preserves causality and maintains the logical structure of existence. The quest to measure gravity's speed has taken us from the theoretical insights of Einstein's equations to the technological marvels of modern gravitational wave detectors. It has required advances in virtually every branch of physics and engineering, from quantum mechanics to general relativity to computational science. The result is not just a measurement, but a validation of our entire approach to understanding the universe through mathematical physics. As we continue to refine these measurements and search for ever more subtle effects, we're not just testing Einstein's theory. We're probing the deepest foundations of reality, exploring the relationship between space, time, matter, and energy that governs everything from the smallest quantum fluctuations to the largest structures in the cosmos. The speed of gravity represents a fundamental constant of nature, and measuring it has taught us as much about the universe as about gravity itself. The hardest experiment in the universe has become routine, opening a new window into cosmic phenomena that were previously beyond our reach. Each gravitational wave detection provides another opportunity to test our understanding of physics, to search for new phenomena, and to explore the mathematical beauty that underlies the apparent chaos of cosmic violence. The universe has always been sending us gravitational messages. Now we can finally read them, and they're telling us stories about the nature of existence itself that we're only beginning to understand. The measurement of gravity's speed stands as one of humanity's greatest scientific achievements, a testament to our ability to probe the deepest mysteries of existence through reason, mathematics, and ingenious experimentation. It confirms that the universe operates according to consistent physical laws, that these laws can be discovered and tested, and that the mathematical poetry of Einstein's equations reflects genuine truths about the nature of reality. As gravitational wave astronomy matures and our measurements become even more precise, we may yet discover subtle effects that reveal new physics beyond Einstein's theory. But for now, the speed of gravity stands as a monument to the power of human curiosity and the extraordinary consistency of the natural world, reminding us that even the most exotic phenomena respect the fundamental principles that govern the cosmos. What if Einstein was wrong? What if gravity could somehow break free from the cosmic speed limit that constrains every other force and phenomenon in the universe? The consequences would be so profound, so revolutionary, that they would require us to rebuild our understanding of reality from the ground up. To explore this possibility is to venture into a realm where the familiar laws of physics dissolve into paradox and contradiction, where cause and effect lose their meaning, and where the very notion of time itself becomes questionable. In our universe, the speed of light serves as more than just a speed limit for objects moving through space. It's the fundamental rate at which information can propagate, the maximum speed at which cause and effect can be transmitted from one location to another. This speed limit is woven into the very fabric of space-time, determining how past, present, and future relate to each other, and ensuring that the universe maintains a consistent logical structure. If gravity could exceed this speed limit, even by the smallest amount, it would create the possibility for effects to precede their causes. Imagine a massive star suddenly collapsing into a black hole. In our universe, the gravitational waves from this collapse travel at the speed of light, reaching distant observers at the same time as the light from the final moments of the star's existence. But if gravity traveled faster than light, the gravitational effects would arrive first, potentially allowing observers to detect the star's collapse before they could see it happen. This might seem like a minor curiosity, but the implications cascade through every aspect of physics. If gravitational effects could travel faster than light, they could be used to send information backward in time. Consider two observers moving relative to each other at high speed. Due to the relativistic effects of time dilation and length contraction, events that appear simultaneous to one observer occur at different times for the other. If faster-than-light gravitational signals could be exchanged between these observers, it would be possible to create closed causal loops where effects precede their causes. The mathematical framework of special relativity makes this conclusion unavoidable. The Lorentz transformations that relate space and time coordinates between different reference frames allow any faster-than-light signal to be used for backward time communication when viewed from appropriately chosen reference frames. This isn't a flaw in the mathematics, it's a fundamental feature of space-time geometry that protects causality by forbidding faster-than-light information transfer. To understand why this matters, consider the famous grandfather paradox. If you could travel backward in time and prevent your own birth, you would create a logical contradiction that threatens the consistency of the universe itself. Similarly, if gravity could carry information faster than light, it would allow the creation of causal paradoxes that would undermine the logical structure of existence. But the consequences would extend far beyond philosophical puzzles about time travel. The structure of the universe itself depends on the finite speed of gravitational interactions. Galaxies form and evolve over billions of years because gravitational influences take time to propagate across cosmic distances. If gravity acted instantaneously, the delicate dance of cosmic structure formation would be completely different. Consider the formation of the first stars in the early universe. As gravity slowly gathered primordial gas into increasingly dense clumps, nuclear fusion eventually ignited, creating the first sources of light in the cosmos. This process depended on the gradual accumulation of matter over millions of years, with gravitational influences spreading outward at the speed of light to gather more material. If gravity had no speed limit, this entire process would have been compressed into a much shorter time frame, fundamentally altering the evolution of cosmic structure. The solar system itself provides another example of how faster-than-light gravity would reshape reality. The precise orbital mechanics that have kept Earth in a stable orbit for billions of years depend on the finite speed of gravitational propagation. If the sun's gravitational influence acted instantaneously, the subtle relativistic effects that fine-tune planetary orbits would disappear, potentially destabilizing the entire solar system. Even more dramatically, faster-than-light gravity would revolutionize our understanding of black holes. These cosmic monsters are defined by their event horizons, boundary surfaces beyond which nothing, not even light, can escape. The existence of event horizons depends critically on the fact that gravitational effects cannot propagate faster than light. If gravity could exceed this speed limit, the very concept of an event horizon would become meaningless. Black holes would no longer be black. Information could escape from beyond the event horizon by riding faster than light gravitational waves, resolving the black hole information paradox that has puzzled physicists for decades. But this resolution would come at the cost of destroying our understanding of thermodynamics, quantum mechanics, and the relationship between information and entropy in extreme gravitational fields. The cosmic web of dark matter that provides the scaffolding for all visible structure in the universe would also be fundamentally different. Dark matter interacts almost exclusively through gravity, forming vast filaments and nodes that guide the formation of galaxies and galaxy clusters. If gravity propagated faster than light, these dark matter structures would evolve differently, potentially creating a cosmos that looks nothing like the universe we observe. Perhaps most profoundly, faster than light gravity would undermine the principle of relativity itself. Einstein's insight that the laws of physics should be the same for all observers moving at constant velocity depends on the existence of a universal speed limit. If gravity could exceed this limit, it would define a preferred reference frame, destroying the beautiful symmetry that underlies both special and general relativity. This would require a return to something like the pre-Einsteinian concept of absolute space and time, where simultaneity has universal meaning and events can be ordered temporally in an observer-independent way. But such a universe would be incompatible with countless experimental confirmations of relativistic effects, from time dilation in particle accelerators to the GPS satellites that depend on general relativistic corrections for accurate navigation. The energy requirements for faster than light gravitational effects would also create new mysteries. In standard physics, accelerating any object with mass to the speed of light requires infinite energy. If gravity could somehow exceed this limit, it would imply the existence of exotic forms of matter or energy that could violate the fundamental conservation laws that govern all known physical processes. These exotic energy forms might allow for technologies that seem impossible in our current universe. Faster than light communication would become feasible, potentially allowing instantaneous contact across galactic distances. Space travel could be revolutionized if gravitational effects could be manipulated to create propulsion systems that exceed the speed of light without violating the local laws of physics. But such technologies would come with their own paradoxes. Faster than light communication would allow the creation of temporal paradoxes on a cosmic scale. Messages could be sent to the past, potentially altering the course of galactic history, or creating closed causal loops that defy logical understanding. The universe would become a place where effect could precede cause, where the future could influence the past, and where the linear progression of time would lose all meaning. The mathematical consistency of physics would also be threatened. The equations of general relativity form a beautifully integrated system where the geometry of space-time determines the motion of matter and energy, while matter and energy determine the curvature of space-time. This self-consistent loop depends critically on the finite speed of gravitational propagation. If gravity could exceed the speed of light, this mathematical harmony would be destroyed, requiring entirely new theoretical frameworks to describe the behavior of space-time and matter. Quantum mechanics would face similar challenges. The uncertainty principle and the probabilistic nature of quantum measurements depend on the existence of fundamental limits to the speed of information transfer. If gravity could carry information faster than light, it might be possible to violate quantum uncertainty by using gravitational measurements to determine particle properties with greater precision than quantum mechanics allows. The cosmic microwave background radiation, the afterglow of the Big Bang that provides our most detailed information about the early universe, would also be fundamentally different. The pattern of tiny temperature fluctuations in this radiation reflects the propagation of acoustic waves through the hot plasma of the early universe. If gravity had propagated faster than light during this epoch, these acoustic oscillations would have evolved differently, creating a cosmic microwave background that bears no resemblance to what we actually observe. Even the expansion of the universe itself might be affected. The current acceleration of cosmic expansion, attributed to the mysterious dark energy, depends on the gravitational dynamics of space-time on the largest scales. If gravity could propagate faster than light, the relationship between matter, energy, and cosmic expansion would be fundamentally altered, potentially eliminating the need for dark energy or creating entirely new cosmic phenomena. The philosophical implications would be equally profound. Our understanding of free will, determinism, and the nature of time would need to be completely reconsidered. In a universe where effects could precede their causes, the notion of making choices and experiencing their consequences would become meaningless. The arrow of time that gives meaning to concepts like birth, growth, aging, and death would lose its significance. Yet for all these dramatic consequences, the universe we actually observe shows no evidence that gravity can exceed the speed of light. Every measurement confirms Einstein's prediction that gravitational influences propagate at exactly the speed of light. The cosmic microwave background, the formation of large-scale structure, the dynamics of binary pulsars, and the direct detection of gravitational waves all point to a universe where gravity respects the cosmic speed limit. This consistency suggests that the speed limit for gravitational effects isn't an arbitrary constraint imposed by nature, but a fundamental requirement for the logical consistency of existence itself. A universe where gravity could travel faster than light would be a universe where causality breaks down, where paradoxes multiply without limit, and where the mathematical beauty that underlies physical law dissolves into contradiction and chaos. The absence of faster-than-light gravitational effects thus represents more than just another confirmation of Einstein's theory. It's evidence that the universe is constructed according to principles that maintain logical consistency, that preserve the relationship between cause and effect, and that allow for the existence of observers capable of understanding the cosmos in which they find themselves. As we continue to probe the limits of gravitational physics with ever more sensitive instruments, we're not just testing the speed of gravity, we're exploring the fundamental requirements for a comprehensible universe, investigating whether reality could be constructed differently while still maintaining the logical structure that makes existence possible. The cosmic speed limit stands as a guardian of causality, ensuring that the universe remains a place where mathematics can describe reality, where experiments can test theories, and where conscious beings can seek to understand their place in the cosmic order. The exploration of these consequences reminds us that physics is not just about describing what we observe, but about understanding why the universe must be the way it is. The speed of gravity, constrained to equal the speed of light, represents one of the deep requirements for a cosmos where time has meaning, where causes precede effects, and where the beautiful mathematical structures of modern physics can accurately describe the behavior of everything from quantum particles to cosmic superclusters. In this sense, measuring the speed of gravity is not just an experimental achievement, but a profound philosophical investigation into the nature of existence itself. It confirms that we live in a universe governed by consistent laws, where the mathematical poetry of Einstein's equations reflects genuine truths about the deepest structure of reality, and where the cosmic speed limit serves not as a limitation, but as a foundation for the logical consistency that makes understanding possible. The universe has a history of surprising us just when we think we understand its deepest secrets. In 1899, the renowned physicist Lord Kelvin proclaimed that there was nothing new to be discovered in physics, only more precise measurements of known phenomena. Within a few years, quantum mechanics and relativity had revolutionized our understanding of reality. Today, as we celebrate the confirmation that gravity travels at the speed of light, we must remember that the cosmos still holds mysteries that could reshape everything we think we know. The next great leap in our understanding of gravity's speed may come from an unlikely source, floating silently in the vacuum of space millions of kilometers from Earth. The Laser Interferometer, space antenna known as LISA, represents the next generation of gravitational wave astronomy. Unlike the ground-based LIGO detectors, which are limited by seismic noise and the finite size of our planet, LISA will consist of 3 spacecraft arranged in a triangular formation, each separated by distances of 2.5 million kilometers. This enormous scale will allow LISA to detect gravitational waves that are completely invisible to current instruments. The space-based observatory will be sensitive to waves with frequencies thousands of times lower than those detected by LIGO, opening an entirely new window into cosmic phenomena. LISA will observe the slow-in spiral of massive black holes over periods of months or years, tracking their orbital evolution with exquisite precision as they spiral toward merger. These long-duration observations will provide unprecedented opportunities to test Einstein's theory and search for deviations from general relativity. If gravity propagates at a speed even slightly different from the speed of light, the accumulated phase difference over months of observation would reveal discrepancies too small to detect in the brief signals observed by current detectors. LISA will essentially use the entire solar system as a laboratory for testing the fundamental properties of spacetime. But LISA's most revolutionary capability may be its ability to detect gravitational waves from the early universe itself. Just as the cosmic microwave background radiation provides a snapshot of the universe when it was only 380,000 years old, a stochastic background of gravitational waves could reveal conditions in the cosmos when it was less than a second old, during epochs when the universe was too hot and dense for atoms to exist. These primordial gravitational waves would carry information about cosmic inflation, the hypothetical period of exponential expansion that occurred in the first fraction of a second after the Big Bang. Different models of inflation